Uh, Today I'm going to talk on applications of evolutionary algorithms for attribute. Attribute selection is very important in chemo and bioinformatics. Future representation and future selection is important in protein function identification. We can represent protein functions, the protein sequences and structures in various types of attributes. Multiple types of attributes with varying numbers in magnitude can be extracted. Only some of these features or attributes will be correlating to the particular function identification problem. Similarly, several attributes can be extracted for gene identification problems. And in quantitative structure activity relationship, we can extract thousands of descriptors and to find out the relationship between the structural descriptors and the activity. So it is important for us to select the most informative attribute and use them in the machine learning algorithms for classification and regression to identify the respective protein or gene functions. It's also useful in finding out the biomarker genes in microarray expression profiles. In several subfields of bioinformatics and chemoinformatics, attribute selection has become very important and very key for the performance of the algorithms. The problem here is, given a set of descriptors, we have to find out whether a given molecule is going to be active or not. Now, the attribute selection problem is to select the most informative subset of descriptors. Is it going to be 1 and 2? Descriptor 1 and 2 is going to be very important, or 3, 4, 5 is going to be important, or 1, 2, and 5 is going to be important. So for a small problem, it may look trivial, but you've got large number of attributes. Selection of the most informative attributes is going to be a really time-consuming and difficult algorithmic problem. Yeah. So attribute selection, there are many approaches. Mainly there are two approaches, which are filter selection ranking approaches and wrapper methodologies. In the filter ranking methodology, we use a given algorithm for only once, and then from that we can extract the ranking information. We can say descriptor 5 is the highest ranked feature, descriptor 3 is the lowest ranked feature. Like that, we can quantitatively rank attributes by using filter ranking algorithms. Whereas the wrapper algorithm, we have to employ machine learning algorithms multiple times, and then we get as the output of the wrapper methodology as the final subset of attributes which correlate to the particular problem at hand. So in the filter methods, we extract ranking information about the attributes. There is no need to repeat a machine learning algorithm multiple times to get this ranking information. It's easy to implement, fast and scalable, but it may not be very accurate. It can provide you some prior preliminary information about the attributes. And to be more accurate, these methods have to be used along with other methods like wrapper methods and hybridize them to get a synergistic combination of filter wrapper methods for most informative attribute selection. So if you have, for the filter methods, if you have 5 attributes in a given problem, if you try to use a very good classifier to make accuracy may not be very good. You rank the attributes by using filter methodology and then find out the most informative attributes and then use an algorithm, you get better accuracy. So there are different filter ranking methodologies like correlation filter. It tries to remove the features which are highly correlated among themselves. So that, because if two features are correlated among themselves, both of them carry the same information. So you need to remove the feature which is having lesser variance. More the variance of a particular attribute, the higher the information it has. We can also use mutual information between the attribute and your output or class information, and then you can get a ranking in terms of mutual information, which is quantitative. And from that, you can select the top ranked attributes as your subset of features from the given data set, and then use any classification algorithm to classify. Information gain is another algorithm wherein you get the entropy reduction by finding out the entropy without using and with using, and entropy reduction in this gives you the information gain quantitatively, and this information can be employed to rank the attributes, and then you can use the top ranking subset of attributes for attribute selection. High-score method is again another methodology, which is feature ranking. It quantifies the lack of interdependence between a given attribute and classification category. So in the wrapper methodology, you have a set of one set of methods. We'll start with the forward selection. The forward selection, we employ only one attribute at a given time and find out that accuracies, and take the highest ranking attribute, and then this attribute is selected. Along with this attribute, we take one more attribute at a time. So two attributes with the first selected attribute, and then with two attributes, one by one, we find out the accuracy and find out which is the best combination of two attributes which gives the best accuracy. We take these two and then we go on, proceed it until all the attributes are included. And after completing the algorithm experiments, we can find out the subset of attributes which gives a maximum possible accuracy. The backward methodology is similar to that, but we start with all the attributes and remove one attribute at a time, which is having the least information about the particular problem at hand. So SVM supported machines provides you an information in terms of the hyperplane. The hyperplane equation, if you have 5 attributes, the hyperplane equation gives you the is given as w1x1 plus w2x2 plus etc w5xy plus b. Each attribute has got a weight. The problem is to find out the best algorithm weights which maximally classifies the particular data at hand. So in the future elimination, we first train the algorithm with all the attributes, find out the weights of each of the attributes, remove that weight which has the least absolute value. The idea is that the attribute with the least absolute value correlates least to the particular problem at hand. So once this is removed, again an SVM algorithm is built with the rest of the 4 attributes. Again, find out the least absolute weight of an attribute and remove it, and so on. So the SVM recursive feature elimination converts. If we got 100 attributes, we have a set of 100 experiments to make. From these 100 experiments, we can find out the best subset. So whereas the original problem is very combinatorially very explosive. If you've got 100 attributes, it's going to be large number of experiments to find out the best subset of the attributes. So SVM is also an embedded method because the algorithm itself is able to provide a feature selection algorithm. We also have other embedded methods, lasso regression and ridge regression, as well as random forest also can provide 2 different feature ranking methodologies. So once we run these algorithms once, we can get quantitatively ranking information from these embedded methods. We can also use an one-norm SVM. Normally, SVM used is a quadratic optimization problem wherein we minimize the 2 norm of the weight vectors. Here, 1 norm weight vector is minimized in 1 norm SVM. In this particular case, large number of weights become very near equal to 0. So by itself, the attributes which are having very small weights can be removed, and this itself serves as a methodology for removing certain attributes which are not important. Yeah. So we have principal component analysis wherein we use a coordinate change, remove the correlation and find out those directions which keep the maximum variance. If you have 100 attributes, we can get up to 100 new directions which are uncorrelated and are orthogonal to each other. The top directions can be found out by solving an eigenvalue eigenvector problem, and these top directions can be used as attributes for selecting as attributes in your algorithm, removing all other directions, and then you get the performance better than the performance of the entire data set. Yeah. So having talked about the other methods, we'll come to the evolutionary algorithms of feature selection. Evolutionary algorithms are very simple to use. They can be stochastic, heuristic, and nature-inspired methodologies. These algorithms do not need to use derivative information, whereas the conventional optimization algorithm, we need to use derivative information, and sometimes it is very difficult for us to formulate a problem as an optimization problem and using conventional mathematical programming methodologies. And sometimes the derivatives may not exist, or it may be difficult to compute. So whereas the evolutionary algorithms are inspired by nature and do not use any derivative information, they can be used. They are very simple to use, but they provide rigorous information. Yeah. The multiple algorithms are there. Genetic algorithm is one example. ACO, swarm-based algorithms, and recently developed black hole algorithms and equilibrium optimization algorithm are quite effective. And we've used many of these methods in our protein and gene function identification problems, and also in chemoinformatics in QSAR models for finding out the most informative attributes. So basic concept is in evolutionary algorithms is to start with a set of trial solutions. The trial solutions for our attribute selection problem is a subset of attributes selected. In this trial solution, so the coding is this chromosome, the coding is a binary coding. We have original data set with 5 descriptors. So once trial solution is descriptor 1, descriptor 4 and 5 are used, so 2 and 3 are not used as per this trial solution. So for this trial solution, we remove descriptor 2 and 3 from our data set and use only descriptor 1, 4 and 5 and use any algorithm to find out the particular performance. Like that, the evolution algorithm start with a set of trial solutions and the fitness is found out. The fitness is here is the performance measure. It can be accuracy or ROC or matching correlation coefficient or F1 measure. Whatever is your current method which is used in your algorithm can be used as a performance measure for fitness. So several such randomly generated trial solutions which reflects different randomly selected subsets of your data set can be generated in the initial generation. Each of them can be evaluated for fitness by sending it to support like vector machines like efficient algorithm to find out the fitness measure, which can be accuracy. So once the fitness measure for the initially generated trial solutions are evaluated, every evolution algorithm uses its own method to get better and better solutions, and with several iterations until convergence, we get better and better solutions, means better and better subsets, giving you better performance measure. And finally, using certain stopping condition, we find out, we come to the best possible subset of attributes. So GA uses 3 different methodologies. GA is a nature-inspired method which mimics the natural evolution. So the 3 methods used in GA are natural selection, crossover, and mutation. So we started with a set of trial solutions. Just now I showed you what is it. Chromosome is a coded form of the trial solution. In this, we have coded it as a 0-1 form. If 0 is there for a given attribute, it is not selected. 1 is there, it's selected. So we start with a set of solutions, evaluate the fitness, and then after the fitness is evaluated, we use the selection methodology, there are multiple selection methodologies are there. Tournament selection says you take any two solutions randomly, whichever is giving less error is selected. These two solutions are removed, and then the rest of the solutions again take any two solutions, select the better solution which is having better accuracy or fitness. Like that, in one set of trial, out of 8 solutions, we get select 4 solutions. Again, the same thing is repeated. Again, we get 4 more solutions. So solutions after tournament selection also will have a similar number of same number of solutions. Number of solutions will not increase, but some solutions would have been selected more than once. Some solutions will not be selected. So once, this is another selection methodology. When the solutions are selected, we use a crossover principle, which is again from the inspired from the natural evolution principle. And so we take any two solutions and then cross them over by randomly selecting one junction, and the new solution is the new first solution. The new child is first part of the first solution and second part of the second solution. The new second solution is first part of the second solution and second part of the first solutions. So before crossover and after crossover, we have different subsets of attributes selected in those solutions. So that means the subset of attributes selected after crossover are quite different. And the principle of GS says you get better and better subsets of solutions after multiple selections of natural selection and crossover. And one final methodology is to mutate. If we use only crossover, select and crossover, our algorithm may come and get stuck up in a local minima. To avoid that, we use a mutation in which, with certain probability, we randomly mutate a solution. So here, the fit blip mutation is select any bit randomly, and if that is selected with certain probability, the probability is very low. If it is 1, the bit is selected to 0. If it is 0, it is selected to 1 after mutation. So this again changes the subset of attributes selected before and after. So using the principle of natural selection, crossover, and mutation, better and better solutions are better and better subsets for attribute selection are generated, and finally we come to a solution which gives you very high performing subset of attributes, which can be most informative, and this can be used for further for all algorithmic purposes. Yeah. So you can also use ant colony optimization. Ant colonies are inspired by the cooperative search behavior of real life ants. If we drop a little bit of sugar at home or workplace, colony of ants come and they come. So the idea is the ants can deposit and sense pheromone. Not only they can deposit pheromone, they get attracted to the pheromone-rich trail. So using this pheromone deposition and sensing, the ants establish the shortest route from the nest to the food and back. And this principle is used. They also try to put obstacles in the path of the ants by creating 2 different paths. By the principle of getting attracted to the pheromone-rich trail, they again get settled to the shortest route. So this principle is used for solving many optimization problems. We also have used in the ACO attribute selection problems. So in the attribute selection problem, what we do is this is similar to traveling salesman problem, wherein a salesman starts with one city and then tours all the cities and come back to the original place. And the problem here is to find out the shortest tour. The feature selection problem makes a subset of tours and then comes out with the best subset of attributes. The principle is similar. So here, the attribute links are deposited with certain pheromone initially. We also use filter ranking information as prior information. Using this pheromone mediated search along with the filter ranking, ants are able to find out better and better tours. So more information you can get it from the our papers, or the original author is Dorigo. So ACO is one such algorithm which has been used in several optimization problems very effectively. I'm not going to the details of ACO. We used attributes ACO feature selection problem for various problems, including epitope prediction, antimicrobial peptides, and several other protein function identification problems. We have found out the subsets of attributes selected by ACO is quite superior to a few other algorithms. We also have used multiple newer algorithms like black hole and equilibrium optimization methodologies. So we will, as I don't have time, so if somebody wants to know about it, you can send me a mail. I can get back to you on this. And I will now go to recent results. So in our recent work, we have used ensemble learning for feature selection. We use ensembles of classifiers using multiple subsets of attributes, multiple parameters, and multiple classifiers. So it improves performance and robustness. Different ensembles of algorithms are used, and by using maximum voting or averaging or weighted average, you can get the final output. So this is a sort of voting methodology averaged over several ensembles. So we can also use bagging and boosting applications for this. So we have used benchmark data sets using diversity measures as an additional performance measure. And we have selected some multiple ensembles which are maximally diverse from one another. And then the combination of these ensembles provides very good performance. We have used different benchmark data sets and protein function identification problems. Recently, we have used the protwork, which is evolved from the concept of the word work, wherein the semantically similar words of similar vector representations. And using this semantically similar words, getting vector representations, we can get for every word an embedding vectors of a particular dimension. Recently, Asghari has used this. By using this methodology, he first annotated manually, and the entire set of Swiss prot sequences were broken into non-overlapping set of k-mers. As an example, this original sequence can be split into 3 different sequences. Every sequence in the Swiss prot was split into 3 different sequences. And using the distributed representation and using a skipgram methodology of neural network, embedding vectors of multiple dimensions and context size. Here, the skipgram methodology uses the word as input and the context as the output. So it will predict the context as the output. And then with this methodology, we can train the model only once and then getting the embedding vectors. These embedding vectors of different context size as well as k-mers and embedding vector sizes can be now used as attributes in different classifiers, and then you can use this for any particular function annotation problem. We have recently used this methodology, and then for antiviral peptides, antifungal and antimicrobial peptides, and then club these embedding vectors at different sizes using our evolutionary algorithm methodologies and selected informative attributes. The performance is found to be very good, and yeah. So because of lack of time, I'm just stop and then project our So this IJCB is flagship journal of Bioclus and ORG, and then we can there are very well reputed 25 and more 25 editorial members are currently serving as editors for the computational biology and bioinformatics community. We invite commentaries, research articles, review articles, short communications, etc. Now, it doesn't have any article processing fee, no publication fee, or no open access fee. Recently, we have invited articles for COVID issues, along with Narendra Sastry, LV editing, whereas managing editors are Aparna and Abhishek. We request all of you to come and submit your articles so that IJCB, we can IJCB provides good exposure to your work. Okay. Thanks a lot for listening to me. I'll be open for questions. Yeah.